Hello everybody, and thank you for joining us here at Nova Biomedical today. My name is Eric Chanel, and I am the Global Product Manager for our Advanced Instruments Osmotech portfolio of osmometers. I'm really excited for this opportunity here to share some of these recent and really critical updates to the United States Pharmacopoeia around osmolality testing, specifically Chapter 785 and the introduction of Chapter 1785. So let's just go over what we're going to talk about today. So I'm going to give a quick overview of the company, of Nova Biomedical, our background and our portfolio. And then we'll move into the recent updates to USP 785, and more importantly, what those changes mean for the day-to-day testing of your labs. From there, I'll introduce the new USP chapter 1785. This is a dense, information-heavy chapter. So rather than covering every detail, I'm going to focus on the sections that have the most practical impact on method suitability, text selection, and data interpretation. And we'll wrap up with the Q&A at the end. I'd love to hear your questions, so please feel free to enter them in the chat. I also have my field application scientist here, Ben Douglas. He'll be monitoring the chat and can be answering some of the questions in the chat directly. As mentioned, if there's some extra time at the end, there should be, so we can answer some there. Any of the questions we don't get to, we'll be able to answer directly over the next day or two as well. So a brief overview of Nova Biomedical and the Advanced Instruments brand. We're a global leader in osmolality testing with over 70 years of experience supporting critical care diagnostics, bioprocessing, cell culture analysis, cell line development, and liquid handling quality assurance. We support customers worldwide with installations in over 90 countries across North America, EMEA, and APAC. Our focus really is on developing technologies that streamline laboratory workflows while delivering confidence and results. So Advanced Instruments specifically, we pioneered freezing point depression osmolality back in, I think it was 1955, essentially establishing the method that USP is still referencing today when they talk about freezing point. While Nova Biomedical built deep expertise across biosensors, diagnostics, bioprocessing tools. And last year, 2025, we merged and brought those strengths together into a single organization that's focused on regulated laboratory workflows. So we offer 5 different product portfolios that serve our customers in the bioprocessing market. Today, the focus is on the regulations that are most relevant to the Advanced Instruments Osmotech portfolio. Osmotech is the only osmometer portfolio that's specifically designed for customers in bioprocessing workflows. They're optimized for testing of biological samples, such as cell culture media, buffers, and aqueous drug product. The other 4 portfolios, briefly, we have the Nova BioProfile portfolio with the Flex2 cell count analyzer. We have the Fast CDV cell viability analyzer. We have Solentum portfolio for single cell cloning assurance. And we have the cell line development instrument workflows with Solentum as well. We have the Artel instruments for pipette and automated liquid handling calibration. And lastly, the Inoximat anaerobic jar system for bacterial cultivation. All our portfolios are supported by their own trained field application scientists and field service engineers. And we have service contract options available for all of them to support. Specifically for the Osmotech ones in the biopharma, we offer qualification and validation services to ensure regulatory compliance like the stuff we're talking about today. Osmotech osmometers, like I said, are designed specifically for biopharma labs, and we built it on basically directly customer feedback. The goal is to make osmolality testing fast, reliable, easy to integrate into existing workflows, regardless of throughput. So the platform offers flexible data connectivity, strong data integrity features, and can be figured to meet your lab's needs. With the Osmotech XT, our capabilities have extended even further, supporting measurements of up to 4,000 milliosmoles, improves performance with viscous or highly concentrated samples. And because the entire portfolio was designed with pharmacopoeia expectations in mind, this provides a natural transition into the topic of today's discussion, what's changed in USP 785 and the introduction of 1785. So first, let's look at USP 785. Now, this is the compendial chapter that defines the formal requirements for osmolality testing. This chapter establishes how osmolality is measured, how instruments are verified, and what laboratories are expected to do from a compliance standpoint. As we go through these updates, I'm going to focus less on restating the full text and more what has changed and why they made those clarifications and kind of what they mean for your routine testing in a regulated pharma lab. So this is the first, but also one of the most important clarifications in the updated USP 785 because it addresses something that labs have dealt with for years, but USP hasn't actually previously stated it this explicitly. USP now clearly acknowledges that different osmometer technologies can produce different results on the same sample. In practice, most of us already knew this, but what's new here is that USP has now formalized that reality into the compendial chapter. And critically, they don't just stop there. They explicitly point readers towards USP 1785 for guidance on how to handle those differences in a structured and defensible way. USP calls out several reasons for why these differences occur. Things like temperature dependence, volatility of certain solutes, and non-ideal solution behavior. These effects become especially pronounced in bioprocess and formulation samples, where matrices are way more complex than the simply aqueous solutions. The practical implication of this update is important. Results generated by different osmometer technologies should no longer be assumed to be directly interchangeable by default. If labs intend to compare values across technologies or switch instruments, for example, USP is now very clear. There needs to be some kind of defined comparison, verification, or equivalence strategy behind that decision if you want to compare. The shift is subtle, but it's meaningful. It moves osmolality away from a sort of a one-size-fits-all assumption towards a more fit-for-purpose model. And that's why freezing point depression is reinforced here for complex and volatile samples, not because other technologies are wrong per se, but because method suitability matters when a sample behavior is not ideal. This concept that method choice matters and that difference that needs to be understood and justified is a theme that's carried straight through the new chapter we'll talk about in a little bit. All right, now we're into one of the more practical updates in USP 785 because it affects how calibration checks are performed, documented, and defended. The central idea is it's simple. The calibration check should be performed in the same manner that measurements will be performed. In other words, your calibration verification should mirror how you generate your reportable results. So a few key points I want to touch on. First, match the calibration check to how you report results. USP now spells out a distinction that labs often handled informally, but now it's an actual requirement. If your method reports individual measurements, say a single result, then calibration check should also be a single measurement of a standard solution. But if you report the mean of multiple measurements, like triplicates, for example, then the calibration check should be performed using that same number of measurements. It means the same N for the calibration check result. So practically, if you have a single result, single check. If you do a mean of 3, you do a mean of 3. So USP is pushing consistency between the way you verify performance and the way you report the sample data. Another key point here is to use manufacturers' calibration solutions. So USP says now that calibration solutions recommended by the manufacturers should be used for calibration. If no manufacturer solutions are specified, then USP points you back to the standard solution list in the chapters table. This is helpful from a compliance standpoint because it reinforces that manufacturer recommended standards are acceptable and even preferred, but it also gives you a fallback if the instrument documentation doesn't specify. Choosing samples that reflect the sample range, another key point here. USP addresses something it's common in audits. Are your checks actually relevant to your samples? So USP provides two different options now. One is using a standard near the center of the range. Option 2 is using a bracketed set where you have two standards, one near the low end and one near the high end of what you're expected to test. So this really pushes labs towards a simple principle. Calibration should be fit for purpose. Again, this is a theme you're going to keep hearing. If you're going to use a wide test range, bracketing makes sense. If you're going to operate in a pretty narrow band, maybe a single middle range would work for you. What's not changed here? It's just worth noting that USP is not introducing a new universal frequency. They're not mandating a specific number of standards for every lab. They're not changing acceptance criteria in this section. This update is really about alignment and clarity, and align the check with how you report results, align with the standards on the manufacturer's guidance, and align with USP and what you actually test. So from a documentation and audit standpoint, again, really useful because it makes your story cleaner, it makes it stronger. So you can clearly state out how results are reported, single versus the mean, how the calibration check is performed, and why you chose a standard or brackets. So continuing on with calibration here. So this update is another example where USP isn't changing numerical limits or adding steps, but it's very intentionally clarifying expectations around what happens when a calibration check fails. The acceptance criteria themselves haven't changed. Instruments still need to be within that plus or minus 4 milliosmol for solutions at or below 400 milliosmol, and within plus or minus 1% above that. What has changed is that USP is now explicitly directing labs to follow manufacturers' recommended troubleshooting when a calibration check fails. Seems subtle, but it's actually a really meaningful change. In the past, there's a lot of gray area around whether labs should immediately calibrate, rerun standards, or frankly, just start inventing their own corrective actions. USP is now saying very clearly, if the calibration check fails, follow the manufacturer's guidance. Then repeat the check. Once the calibration check is successful, the instrument's ready to use. From a practical standpoint, this aligns with how labs already operate, typically. It doesn't change the workflow, acceptance limits, or calibration frequency. It just formalizes the role of the manufacturer's guidance within the compendio process. Again, from an audit perspective, this really helps you. It gives you a clear USP-endorsed corrective action pathway rather than having to justify why you followed the user guide or invented sort of a site-specific workflow or workaround. So again, this is all about consistency and defensibility. USP is reinforcing that calibration failure should not be addressed using, or should be addressed using the defined, validated manufacturer procedures. Still around calibration. With this update right here, USP is focusing on making expectations clearer for when calibration checks should be performed. What they're saying here is that calibration checks should be based on how the instrument is actually used and that they should be performed prior to sample analysis to ensure accurate results. And I want to be very clear here about what they are not saying. USP is not mandating a fixed calibration frequency. There's no new requirement to calibrate daily before every run or on some universal schedule. Instead, USP is intentionally leaving this as a risk-based and lab-defined. The expectation is that labs define and justify calibration check timing in their SOPs based on specific factors, like instrument utilization, sample volume, and prior performance. For most labs, this probably doesn't require any operational change. Doesn't mean running more standards or more checks. It just mainly affects how your procedures are documented and justified. The emphasis is on demonstrating that calibration is verified at appropriate times to support confidence in those reported results. This also aligns well with our manufacturer's guidance, where calibration and verification is typically recommended prior to routine testing, and calibration is performed only when the verification fails. From an audit perspective, again, this clarification really helps you. It gives you a clear rationale to follow. So calibration checks are tied to instrument use, result generation, and not some arbitrary calendar frequency. Now, at first glance, this one looks like a huge update. I know there's a lot of text in this test solution section here, but in reality, USP is actually just reinforcing something that many labs already understand, just never spelled out that clearly. And that idea is that dilution is not a neutral step in osmolality testing. Once you dilute a sample, you may not be measuring behavior that's directly proportional to the original formulation anymore, so it can distort your results. As a result of that, USP continues to be very explicit that testing samples neat or undiluted is preferred whenever possible. That has been and continues to be the assumption now. Dilution is still allowed. The USP isn't prohibiting it, but only when it's truly necessary. And when it's necessary, it needs to be justified as part of the method development, qualification, and validation. A really important clarification here is you simply can't apply a dilution factor to back calculate to the original osmolality unless you've demonstrated linearity between dilution and osmolality. This is a major change because previously there was no caveats. The back calculation was forbidden, flat out. Now labs have some options if needed. What they're saying is that if you haven't shown osmolality scales linearly with dilution for that specific formula, then you need to report osmolality of the diluted sample as is, not assume that mathematically you can recover the neat value. And that gives labs more flexibility, but also really clear direction when deciding how to handle it and how to report here. And when dilution is required, USP raises expectations around control. Dilution should be kept to a minimum and performed using techniques that reduce handling error, things like gravimetric dilution and positive placement pipettes, especially for viscous or complex formulations. Now let's look at something a little different. This is not about something that USP added, rather it's what they removed. So previously, USP listed some very specific examples of why a sample might fail to freeze when using a freezing point osmometer. Things like high viscosity, mixing speed, amplitude settings. That language has now been taken out. By removing these prescriptive root cause examples, USP is intentionally stepping away from instrument-specific guidance and moving toward a more, I guess I would say, outcome-based expectation. The focus is no longer on why freezing mechanics failed, but whether the solution freezes reliably and produces accurate results. Practically, this means that if a sample fails to freeze consistently, results may be inaccurate, and the system should be optimized before reevaluation and recalibration following those manufacturer-defined procedures. I'm a big fan of this change personally, because it improves the technology neutrality and audit defensibility. And it aligns well with modern instruments where troubleshooting optimization are best guided by the manufacturer rather than following this non-exhaustive list of generic parameter descriptions. This is another example where USP isn't changing the fundamentals of freezing point osmometry, but is tightening expectations about how labs think about sample prep and troubleshooting. USP is clarifying that interfering elements, things like insoluble particles, emulsified droplets, or trapped air, don't necessarily change the true osmolality of the aqueous phase. However, even if they don't change the osmolality itself, they can interfere with the freezing process and impact the reliability of that measurement. So in practice, this is something that many labs have experienced. A sample that looks fine chemically may still behave poorly because of bubbles, because of droplets or particles, disrupting that crystal formulation. Like I bet some of you in the session have had a troubleshooting call discussing this topic to figure out the best way to go through this solution. So now USP explicitly states that if those interfering elements affect the ability of the sample to freeze properly or produce reliable data, they should be removed, for example, by centrifuging. And the osmolality of the clarified aqueous phase should be measured and reported. What's important here is that USP is enforcing it's just good analytical hygiene. It's not inducing or introducing any new requirements. It also aligns with the broader theme, which we've been discussing throughout, and will continue to, that method suitability matters. It's not about just generating a number anymore. It's you need to understand why a result is reliable and to be able to defend how that sample was handled. Lastly, for USP 785, we have a small change to the tonicity section. Simply adding a note that the new chapter 1785 is there to talk about tonicity. As this relates to your testing, it doesn't really have much of an impact. But I will say it does provide a perfect transition for us to start the conversation about USP 1785. So up until this point, we've been talking about 785, which is the compendial chapter, the chapter that defines the formal requirements for osmolality testing. Now we're going to look at USP 1785, which was introduced just to add context around those requirements, not to replace them. Where 785 focuses on what needs to be done. 1785 offers background information, workflow templates, which can be applied in practice, especially when samples don't behave ideally. And just to be clear, 1785 is an informational chapter. It doesn't create any new compliance requirements, but it does provide useful guidance around method suitability, technology selection, and known measurement limitations. All sorts of good information, but without the pressure of compliance. I find this information to be particularly relevant and useful as formulations become more and more complex and really don't always look or behave like simple aqueous samples that many of us started with. So next, we're going to walk through 1785, how it frames these practical considerations, how labs can use that guidance to support their decisions, and some of the data that we've actually generated supporting Osmotech portfolio osmometers for use with difficult samples. All right, before we dive into the section, I do want to pause for a moment and just orient to everyone to how USP is structured as a chapter. USP is 1785. 1785 is an informational chapter. Again, it's not introducing any new compliance requirements. Instead, it's meant to provide scientific and practical context around osmolality testing, particularly when real-world samples don't behave ideally. Interestingly, if you think back to what we're talking about 785, it was only referenced twice. 1785 was referenced 2 times only, and that was in the considerment for instrument selection and also that brief mention of tonicity that I just showed you. So it really, that alone shows you it's the supplemental information chapter. Also, there's a quick rule of thumb when it comes to USP chapters in general, which is general chapters numbered below 1,000 are compendial requirement chapters, while chapters above 1,000 are general information guidance. So the numbering alone, again, is just reinforcing that it's a framework for testing suitability and interpretation, not any new mandates or procedures. Now, this is a dense, dense chapter. We're looking at 15 pages of information. So I'm going to be pulling out the most critical parts here for you to pay attention to. With that in mind, let me just give you a quick overview of the structure. So the chapter starts out logically with an introduction and background, focusing almost exclusively on freezing point technology basics, how osmolality is calculated, and why the concept of osmolality coefficients matters. This is where the USP lays the foundation for understanding ideal versus non-ideal behavior. And we're going to get a lot into that. From there, USP walks through different sources of non-ideal behavior and provides a framework for recognizing which effects are most prominent in any given formulation. Once that groundwork is laid, the chapter shifts into instrument-focused guidance, actually. This includes considerations for instrument selection and how USP 785 fits into that decision-making. Also, some information on tricky sample types and methods for how to evaluate whether two measurements are statistically different or truly equivalent. USP then connects those concepts back to practical pharma use, why osmolality matters in development and manufacturing, and how it's used as an in-process control. Finally, the chapter closes by addressing osmolality and tonicity together, reinforcing that while they're related, they're not interchangeable concepts. So as we move through the next few slides, the goal isn't to cover every equation or theoretical detail, but to pull out the practical takeaways of how USP suggests labs think about method suitability, instrument choice, and rationale when testing these increasingly complex formulas. All right, so with that in mind, let's look at how the chapter addresses this. So we start off with a background chapter. As I mentioned, it's pretty much entirely focused on freezing point. So it's full of information about freezing point, how it works, potential challenges and improvements, and more. I suppose the level of detail is not surprising for an informational chapter, which specifically calls out freezing point as the primary method for osmolality testing in pharma. So look at figure 1, which shows us the two models of different freeze curve behavior. In a nutshell, this is the principle behind freezing point osmometers. The sample is cooled below its freezing point, freezing is triggered, and as ice forms, you see that temperature rise until it reaches a stable freezing plateau. That final stable temperature is what is used, or should be used, to calculate osmolality. For simple aqueous solutions like salt standards, for instance, it happens quickly and cleanly, and everything behaves pretty close to ideal, like you see in that little orange line, the solid orange line. But real pharmaceutical samples, they don't behave like that. USP 1785 gives us insight into a few sources of non-ideality that can change this curve. Things like solute water interactions, solute interactions, high concentration, and viscosity. All of these factors can slow freezing, stretching out that plateau, and can change how cleanly equilibrium is reached, which is represented by that dotted line that you see in figure 1. And that's important because if an instrument doesn't actually wait long enough or use software to detect the true plateau before taking a measurement, that's when you start to see bias. Now think about the types of products which you are manufacturing. And you'll realize that many of these products have multiple different complicating factors. So you're probably not going to be seeing that ideal freeze curve. So please just keep that freeze curve in mind as we move through this chapter, and you can see how it impacts these different complexities. Now, I need to warn you here. That's why I'm taking a drink of water. This is a lot of information being summarized in a single slide here. I'm skipping over all the mathematical formulas, and I'm just going to focus on the high-level concepts and why they matter to you. Basically, this entire section, calculations of osmolality and osmolality coefficient, is reminding labs that real formulations don't behave ideally. And that matters when you start interpreting results. The big takeaway from all this is you should not automatically assume that osmolality scales linearly with concentration, especially with complex formulas. You know, products with high protein, high sugar, high viscosity, or multiple component formulations. The information provided is aiming to help labs avoid false assumptions. Calculated osmolality is a derived estimate. It's not a measurement, and it can be really misleading if non-ideal behavior isn't understood and accounted for. USP is calling out that changes to formulation, even subtle ones, can shift measured osmolality in ways that aren't obvious from composition alone. This is why we always recommend measured osmolality values over calculated values. This is also why the guidance emphasizes documenting assumptions and being thoughtful when you dilute samples, trend data, or compare results across formulations or concentrations. So the point of this entire section here isn't to make you redo calculations. It's to encourage labs to, I guess, frankly, ask smarter questions. Do these results behave the way I would expect from this formulation? And when the answer is yes, that's good information. When the answer is no, it doesn't mean that the measurement's wrong. It may be telling you something real about the sample. 1785 wants you to understand that non-ideal behavior is normal and it's expected. Once you understand that, we can move on to talk about method suitability, instrument selection, and the rest this chapter has to offer. So I'm going to take a couple minutes just to understand the non-ideal behavior a little more before we move deeper. So this is a brief breakdown of why different solute types deviate from ideal behavior and why that matters for freezing point osmolality measurements. For non-electrolytes, like sugars, the dominant effect is water binding. These solutes strongly hydrate, which reduces free water and drives osmolality higher than calculated predictions. But electrolytes behave differently. So here we have competing effects. Electrostatic attraction between ions tends to lower osmolality, while water binding pushes it higher. The net effect really just depends on concentration, which is why electrolyte solutions often show this really nonlinear behavior. From a practical standpoint, freezing point osmometers that do not have intelligent freezing, which is what our Osmotec XT has, are more prone to bias due to the hydration effects and the slower freezing in the non-ideal solutions. Think back to that slow freezing curve we looked at before. This is why USP provides sample testing approaches like dilution studies, plotting measured osmolality value calculated, and looking at reasonable trends in the osmolality coefficient, which is a measure which quantifies how far a real solution deviates from ideal behavior, rather than looking for a perfect agreement. What you need to remember is that deviations from ideality are expected. It's expected solution behavior. They're not errors. Understanding the dominant interaction just helps you interpret the results correctly and decide whether any additional verification is warranted. Another useful piece of information in this section is the dilution-based methodology, or DBM. It's a practical way to verify osmolality measurements when formulations contain mixed or unknown sources of non-ideal behavior. No, this is not a recommendation for diluting sample for final testing. The goal here is just to understand how the sample behaves across concentrations. It's a pretty standard dilution structure, which probably many of you are familiar with already. Workflow starts at the highest concentration, like the worst case sample, followed by a controlled series down to a low osmolality point where it can be treated effectively as ideal. The lowest point is used to estimate an effective molecular weight, which allows comparison of measured osmolality to calculated ideal behavior across the dilution range. What we're looking for is smooth, physically reasonable lines. If measured values sit above the ideal above the ideal line, water binding is likely dominant. If they sit below, solute interactions are the more prominent one. The key takeaway is that the DBM gives labs a useful framework to confirm whether freezing point osmolality data are behaving as expected, especially for these complex formulations, without assuming ideality or relying on a single measurement point. That way of thinking leads directly into the next part of the chapter, where USP shifts from theory into practice, looking at how non-ideal behavior informs instrument selection, method suitability, and some pathways for verification. All right, up until this point, we've talked about non-ideal behavior, why the different solutions behave differently. Here, USP applies that understanding to a real question that you all will face. Is this osmometer suitable for this sample? Now, section really reinforces this idea that instrument selection should be driven by sample behavior, not assumptions of ideality or interchangeability. So with that in mind, let's look at how USP translates those principles into specific recommendations per sample type. So this table is actually pulled directly from the chapter. I will say I did make it look a little nicer though, but the text is all what's directly in the chapter. This is the point when USP 1785 takes all the theory we've talked about and turns it into some practical guidance. So they're very clear that the instrument selection is not a one-size-fits-all thing. It should be driven by sample behavior, not just by what an instrument happens to be capable of on paper. The table organizes common sample types down the left, then lays out recommended measurement approaches, potential challenges, mitigation strategies. Importantly, and I know I've said this multiple times already, but this is a guidance. This is not a mandate. For low viscosity aqueous solutions, USP notes that while freezing point and vapor pressure methods may be suitable, because these samples tend to behave more ideally, freezing point is still the preferred method for osmolality testing in the pharma industry. As formulations become more complex, for example, with hydrochloric acid systems or containing volatile ingredients, USP reinforces that a preference for freezing point depression because these volatile components can evaporate during vapor pressure measurements and bias results. USP spends then quite a bit of time calling out PEG-containing systems, high concentration polymers, protein-rich formulas. Because freezing behavior with these products becomes slower and less predictable, which increases the risk of measurement bias or just outright freezing failure. Think back to that chart with the two freeze curves we talked about. I showed a few minutes ago, and the one that was slow and fast freezing. And understand that non-ideal freeze curve is more representative of this type of product. It's very similar to that. And that's where you see repeated language around samples not freezing, freezing inconsistency, or showing unacceptable variability. USP acknowledges that these are known physics-driven challenges, not user error. That said, improvements in technology have taken these challenges head on and have reduced their impact significantly. And I'm going to show you some data on that pretty soon. For very viscous or gel-like samples, USP also highlights practical handling concerns, like entrapped air or poor thermal equilibration, and recommends strategies such as smaller sample volumes or removing air, again, focusing on suitability rather than some sort of rigid rules. USP also makes an important distinction for emulsions and suspensions. The components in these samples may not change the true osmolality, but dispersed material can disrupt freezing. So USP suggests measuring the clarified continuous phase when needed. And while there's no direct callback here to 785, it does perfectly align with the interfering particles update to that chapter we spoke about before. Finally, 1785 tells us that some samples just aren't appropriate for osmolality measurement at all. Things like non-aqueous formulations, water and oil emulsions, or solutions that are outside the measurable range. In those cases, USP points users towards either alternative approaches or diluting sample to bring it in range. The overarching theme is this table is that when measurements become challenging, labs should strive to recognize limitations, apply mitigation strategies, and verify that suitability. So I know I mentioned I'm going to show you some data supporting the improvements that were made for testing challenges. So let's take a couple minutes here to provide some context for these recommendations. I'm going to give you a little bit of a peek behind the curtain and show you some of our testing data using the Osmotech XT with these different challenging sample types. Okay, before we get into the really messy sample types, I want to start with a baseline. This shows low viscosity carbohydrate solutions, sucrose and glucose, made up in both water and saline, measured across a pretty wide concentration range. The main point here is that for these clean samples, you can see exactly what you'd hope for: smooth, predictable increases in osmolality concentration as goes up. Or smooth, predictable increases in osmolality as concentration goes up. What I like about this here is that there's no weird jumps or surprises. It's steady, it's consistent, which is what you'd expect when the matrix isn't fighting you. It's also worth calling out that you can see that we're getting results well above 3,000 milliosmoles with the Osmotech XT at the high end of some of these conditions. This is the extended range, which we actually go up to 4,000, is one of those major improvements that we've made to overcome the challenges of testing complex samples. It's also a nice lead-in for some of the later data sets where range and freezing behavior starts to matter more. So think of this almost as like our control data. It shows that when a sample is relatively straightforward and behaves in a very predictable way, while not as simple as like a plain salt reference standard, it's low complexity compared to many of the product types that you all produce every day. And now that we got that baseline, let's look at the next slides. It would show some of the changes as we move into really challenging formulas and how the sample freeze plays a role. All right, remember how USP 785 made this statement that different osmometer technologies can give different results on the same sample? Well, this data set here does a really nice job of illustrating that point in a few different ways. First, this is a great example of slow freezing versus fast freezing concept leading to bias, which we talked about earlier. These samples are cryoprotectant media, so they're the exact kind of formulation that behave weirdly and can freeze slowly, that supercool differently, and the matrix can take longer to reach that clean equilibrium plateau after nucleation. And that's where the bias problem shows up. If an instrument doesn't wait long enough for the true equilibrium freezing point, it grabs the temperature too early, before the plateau is established, and you end up with a systematically high bias, typically about 10 to 30 milliosmoles in my experience. This is what you see when you look at the freezing point 1 and freezing point 2 results shown here on the graph, roughly 25 milliosmol higher than what we see with the Osmotech XT with its intelligent freezing that's waiting for the true plateau. Second, we're also seeing that volatile ingredients can create method-dependent offsets, especially when we look at vapor pressure approaches. In these data, you can see the pattern clearly. The vapor method trends are way lower. That's expected for formulations like this because vapor pressure osmometers are sensitive to these compounds. In these products, the volatile compounds partially or fully evaporate during measurement, resulting in a final value that is truly missing key components. That's why really only freezing point depression is recommended for products that contain volatile components. Now, tying this back to freezing behavior, what I really like here too is the precision that you see with the Osmotec XT. You're seeing tight repeatability, a mean of just under 1 CV on average, even at high osmolality. And that gets to the improvement story when it comes to slow freezing sample types. A WIN is an instrument that can freeze reliably and give the sample enough time to equilibrate instead of rushing to a result. And now this concept is actually directly called out in 1785. And when they say, and I quote here, in other cases, the instrument may produce a result, but that result may be systematically biased towards the higher than true osmolality due to taking the value prior to achieving true equilibrium at freezing temperatures below the true equilibrium. Newer instruments may have improvements that allow for more reliable freezing and provide more time for equilibration to occur, end quote. So these data illustrate that perfectly. So this slide really enforces 2 points. For volatile cryoprotectant sample types, freezing point depression is the method of choice. And for freezing point measurements, waiting for the real plateau is what helps you avoid that early read bias. And that's where the intelligent freezing in the Osmotec XT really shows up. All right, from here, let's keep building on the theme of some difficult matrices. Now let's look at the PEG-containing formulations, which USP 1785 specifically highlights as samples that can exhibit non-ideal behavior and challenging freeze characteristics. PEG systems are a good example of why USP is emphasizing method suitability rather than ideal linear behavior. PEG strongly interacts with water, which can alter freezing behavior, and in some cases, challenge freezing point measurements if the instrument isn't designed for it. What these data here demonstrate, though, is that across testing concentration range, osmolality measurements on the Osmotec XT behave in a stable and predictable way, with tight precision maintained even as the concentration increases. The takeaway here is not that PEG formulations are trivial to measure. In fact, it's quite the opposite. They are seen as one of the more challenging sample types. But what I want you to see is that when measurements are performed with an instrument that's designed for complex matrices, whether it's fit for purpose, you can get reliable and consistent results. And with that context, we can move on to another challenging sample type, which is the high polymer and protein formulations, where viscosity and freezing dynamics become even more pronounced. What we're looking at here is data using BSA as a representative protein system, measured across increasing concentrations in both water and saline. These are the exact kind of samples where labs often start to see issues, slower freezing, higher variability, and inconsistent results, especially as concentration and viscosity increase. Heck, I've run into situations where labs were using older freezing point technology and with a high protein product, and they were running into so many issues with inconsistent results. Thankfully, we were able to resolve their headache entirely by having them adopt the Osmotec XT. I won't call it any specific names, but if you're on this call and listening, you know who you are, and I'm glad we were able to help you. What's important, though, in this data is that across both matrices, the Osmotec XT produces consistent and precise osmolality measurements over a broad concentration range. And you can see that variability stays low even as concentration increases, which tells us the system is capable of handling non-ideal behavior and slower freezing characteristics. Data set here highlights another different sample type, which was called out in that table, gel and high viscosity formulations, where freezing behavior is also sample handling, and also sample handling become limiting factors. USP actually acknowledges that in these product types, the freezing point measurements can be problematic because viscosity, entrapped air, slow heat transfer can interfere with reliable freezing. So what we're showing here is that data generated using high viscosity formulations, including semi-solid gels, these are exactly the type of samples that USP flags as potentially difficult. Despite those challenges, freezing point depression on the Osmotec XT produced precise and reliable measurements, demonstrating that these samples can be measured successfully when the instrument and the methods are matched to the matrix. This aligns directly with what 1785 is talking about with this concept of method suitability. The question isn't, can osmolality be measured, but rather, can it be measured reliably and appropriately for this sample type with this instrument? And just as a side note, this work is actually summarized in a white paper that's available on novabiomedical.com if you want more detail. From here, we'll shift back to 1785 guidance itself and talk about the verification, when verification could be a good idea, and some workflow templates for demonstrating that the osmolality method is suitable for real laboratory conditions. Okay, section 3.1 is really about when it makes sense to consider verification testing. USP 1785 is clear that this isn't something you need to do routinely. There's no expectation to constantly re-verify a method that's already working. But when something changes, that's when verification becomes a useful tool. And those change points are things you probably already recognize immediately: a new instrument, a new lab, a new analyst, or just a new sample type. The reason's really straightforward. Osmolality testing is performance sensitive, and it changes in instrument sample handling or in techniques, and that can show up in the data, especially with more complex, non-ideal samples. So the intent here is practical. When you rely on these measurements to make decisions, you want the confidence that these results are still behaving the same way under your current conditions. So keep in mind, this doesn't mean a full validation. We all know how burdensome and full validations can be. Most of the time, this is a simple focused check, often just a short precision study to confirm that nothing meaningful has shifted. So for end users, the takeaway is balance. You don't need to overtest, but you also shouldn't assume that everything is interchangeable when something changes. So if you decide to do a verification, if you decide that verification is a worthwhile step, the obvious next question is, what does these actually look like in practice? And that's what that next section is going to walk us through. So section 3.2, it's a template for verification procedure that focuses on how measurements behave in normal everyday testing. The question USP 1785 is asking here is, does this osmometer give consistent results for this sample the way you're actually running it in a lab? So they suggest using undiluted sample if possible and running a small set of repeat measurements, 6 replicates, for using that standard 785 approach. There are two main things to look at here. First, does the measurement work reliably? So no freezing failures or errors. Excuse me. And the second, is the variability reasonable and in line with what the instrument is expected to deliver? The stats on the slide are just a good structured way to answer that question. If the results are consistent, you're good to go for that sample. If not, that's useful information. It may mean that the sample needs different prep, dilution, or just different measurement approach. So the takeaway here is that verification is a simple and is sample specific. It's just a way to confirm your osmolality results make sense for the material that you're testing. And that leads nicely into the next section where USP talks about what happens when you start comparing instruments or methods and how to decide whether results are simply different or interchangeable. So it's about one specific situation here. When you're comparing two osmolality measurements and you want to know if they're meaningfully different. USP 1785 gives a structured way to think about it, but the decision path itself is actually pretty simple, frankly. Step one is precision. If the two methods don't behave similarly from a variability standpoint, you stop right there. USP's view is that if precision doesn't line up, comparing averages doesn't tell you much. If the variability does look comparable, then you move on to step two, which is comparing mean values. If the comparison shows statistically significant difference, the takeaway is not that one method is wrong versus the other. It just means that the results shouldn't be treated as interchangeable. That's really the key point of this whole section. This analysis about identifying differences, not trying to force agreement. And just to reiterate something I've said a few times, this is optional. USP isn't telling labs that they must do this. In 1785, they're simply sharing a reasonable approach for comparisons if you're already in a situation when you're comparing instruments or methods and you'd like to understand whether the results can be treated the same. I've gotten this exact question from end users, especially with complex samples, where they see a difference between instruments and immediately worry that the new instrument is not compliant. And that's not what USP is saying here. The point is differences can be real and expected. Just we talked about behavior being strange with non-idealities. It's real and expected. And if this interchangeably matters, USP is giving you a structured way to evaluate it. So at the end of this process, you're left with a clear outcome. Either the two methods behave differently and should be treated separately, or you move on to the next question, which is, can they be treated as interchangeable? So the section continues down that path that we've established previously, where you want to switch instruments, add a second osmometer or transfer method, and still use the same specs and trends. And you have found that the results are not different between the two osmometers or methods, and you want to treat those as interchangeable. Now, what's the best course of action? USP is very clear here that equivalence is a higher bar than just checking for differences. Because of that, this template gathers more data and has a tighter criteria. But again, only when equivalence is your goal. And if that's the goal, USP proposes this workflow, assessed using a toast approach to demonstrate equivalence. If variability between methods doesn't line up, USP's guidance is simple. Just don't call them equivalent. That's straightforward. It doesn't mean that one method is wrong. It just means they should be treated separately. For end users, the implication is flexibility. Equivalence testing is optional, but it can be useful for if you want operational simplicity, of course, shared limit, shared trending, shared data decision making. But if you don't need interchangeability, you don't need this level of analysis. So the big message across these sections is it's choice. If the results are different, document it. If the results need to be interchangeable, this is one structured way USP suggests for demonstrating that. And that really helps close the loop here on section 3. And it helps labs decide how much of a comparison is appropriate based on what you actually do. Up until this point, we focused on how osmolality is measured, how non-ideal behavior can influence results, and how 1785 frames method suitability and verification. In this next section, USP shifts the focus to why osmolality matters in pharma development and manufacturing, and how it's actually used to support real decisions. The section is actually less about analytical theory and more about like practical application theory, I guess I'd call it, and how osmolality fits into formulation development, process control, and release strategies. So the information in this chapter is probably very familiar to everyone on this call. None of it should be overly surprising. Personally, I think this section would have made a whole lot more sense to start at the beginning of the chapter in order to lay the foundation of why osmolality testing is useful for pharma industry, but that's neither here nor there. But actually, this inclusion chapter really does highlight just how, the informal and informational nature of this chapter. It's nothing actionable. It's just background information. So I won't spend too much time on it. Basically, osmolality has been used in the pharma industry for development and manufacturing for a long time. And the way USP frames it here is largely reflects how labs already think about it today. During development, osmolality teams helps teams understand how a formulation behaves. Once you move to manufacturing, the focus shifts a bit. Now it's about process consistency. Osmolality is commonly used as in process control and release attribute. It's also used for testing buffers because, unsurprisingly, buffer osmolality directly impacts final product osmolality. There's also a suggestion that for more challenging formulations, like high protein products, end users may want to focus on precision and repeatability rather than absolute accuracy. Now, I want to challenge that statement. Given the robust data I showed you a little earlier with the Osmotec XT, with the right freezing point instrument, you don't actually have to sacrifice accuracy for precision. So it's a little bit of an outdated thing, which kind of contrasts what they've also been talking about earlier in the chapter. Overall, USP is not changing how osmolality is used. It's just reinforcing that osmolality remains a practical, widely used control parameter, and that its value depends on understanding how and why the numbers and results behave the way they do. This last section shifts gears slightly. It's less about how to measure osmolality and more about how osmolality results should be interpreted. USP uses this section to reinforce that osmolality and tonicity are related, but not interchangeable concepts, and that distinction matters when osmolality data are applied to pharma decision making. So this is another one of those probably well known to people on this call, but it's worth spending a minute on because USP clearly wanted to reinforce it. If you recall, this was one of the 2 direct callouts in USP 785, so we should spend a minute on it here. The big message is simple. Osmolality and tonicity are related, but they're not the same thing. Osmolality tells you about a solution, how many solute particles are present. Tonicity tells you about the biological response, what happens when that solution interacts with a cell. That difference matters because not all solutes behave the same way biologically. Only non-penetrating solutes really drive tonicity. Penetrating solutes may affect osmolality, but they don't necessarily change the final cell's response. So that's why the 2 solutions with the same osmolality can behave very differently in vivo, and why osmolality by itself shouldn't be overinterpreted as a direct measurement of biological impact. USP also uses this section to explain why formulations tend to avoid strong hypotonicity and why hypertonic solutions are often better tolerated than hypotonic ones, depending on the route of administration exposure. For formulation teams, this mostly serves as sort of conceptual guardrails. Osmolality is important and widely used measurement, and it's only one piece of the puzzle, though. So the takeaway here isn't a new testing protocol or anything like that. It's just a reminder to use osmolality data in the correct context, especially when thinking about tonicity, tolerability, and formulation design. And that wraps up 1785. So what did we learn today? The updates to 785, the compendial chapter, didn't fundamentally change osmolality testing. They've clarified expectations around execution, documentation, and defensibility. we now have much clearer guidance on calibration checks, how to respond to failures, sample handling, the appropriate use of manufacturer recommended procedures, which makes things easier for your SOP and defending. USP 1785 then builds on that foundation. Again, I've said it a few times, but I'm going to reiterate it. It's the informational chapter, not a set of new requirements, but it does provide practical guidance on method suitability, instrument selection, data interpretation, especially around those complex and non-ideal samples, which we got a lot of really good information on. A consistent theme across both chapters is that non-ideal behavior is expected in real biopharma formulations. Proteins, polymers, PEG, volatility, and viscosity all influence freezing behavior. And USP is encouraging labs to understand why results behave the way they do, rather than forcing ideal assumptions. And in case you couldn't tell, I absolutely love that this is finally being addressed. It's been something that's come up a lot over the years, and I'm really, really glad to see it formally written in. And finally, throughout both chapters, freezing point osmolality is reinforced as the preferred and most robust approach for biopharma samples, particularly for complex matrices, because it measures the total solute behavior and delivers reliable, defensible data. And with that, we have a few minutes left here. I will take some questions. Let's see. Ben, you can jump off mute if you want to let me know anything specific, or I can look through the chat as well.
No worries. Yeah, so we had one that came in a few minutes ago relating to guidance for calculating theoretical contributions from MAB protein molecules at different protein concentrations. Is there anything specific in the guidance that...
So that would be diving pretty deep into it, but in chat, I believe it's section 2 in the background chapter, there's a calculations for osmolality and osmolality coefficients. Does go into a lot more specific about the different interactions and ways to account for that. So that would be, I can point you to that chapter or take that offline and we can go through that, but that's that is addressed in the chapter.
Yeah, one that just popped in. Can we get your interpretation of what the near center of the expected range means now for selecting a calibration check standard? This requirement has changed over chapter version updates. Previous versions used to need to be plus minus 50 of the sample, then bracketing within 300. Is this still used, and what is the flexibility allowed for this decision?
So in terms of, there's a little bit two different questions here. So in terms of determining the range, you're going to look for that middle point of what your expected range is. So for example, say you have 200 to 300, you'll aim for 250, but as close as you can find within that. Not every solution is available, every standard is available. And to the question about whether you need the 300 check after, that is no longer recommended by the pharmacopoeia. That said, if it's in the manufacturer's recommendations, that takes precedent. And that's sort of what the whole new situation is about here, where they're saying, if the manufacturer recommends it, that should be sort of the source of truth, the first line, the default choice. After that, you can move to a different one. Any other questions, Ben?
Yep, one actually just popped in. Is osmolality a limit test?
In what sense? I'd want a little more context. So I guess it would really depend on what you're using it for. So say you have it as a release test for your product. If you have a set range that's required to be within and you've determined that that's critical for your release criteria, then yes, it would be. Often that's where we'll see it, but we will also see it applied in many other situations, manufacturing, formulation, where you're really looking for trending and just looking for process controls. And so you're ensuring that it's not with, deviating and there's no changes in that sense. But as it can be used as a final release criteria as well.
One more just popped in. What's the lower limit for hypotonic formulations for SC administration?
Sorry, say again, Ben? I was reading another question.
What are the lower limits for hypotonic formulations for SC administration?
I am not sure off the top of my head. I can look at that though and find out for you. One question I just saw, so the popped in is Osmotec XT more precise as compared to the Osmotec Pro multi-sample? It is. It also has a higher range, so it's not directly apples for apples comparison. We're able to do, with the XT, we're actually able to double that range up to 4,000. So there's some differences at the higher range, but other than that, no.
Just came through. What is the required amount of replicates for samples? I've seen 2 and 3.
So the requirement for replicates, so 3 would be default. There, if you're doing the comparison, though, it would be 6, which is one of those things that's defined. See, I think it was back. I could jump back to the slide, but in the verification, that's calls back to 6 replicates for doing a direct comparison. But if you're just doing your own replicates, it would be 3.
One more related to the Osmotech Pro versus the XT. Does the Osmotech Pro fit for these? Is the Osmotech Pro fit for these complicated formulations?
It's a great question. To an extent, yes. And so what we've seen is that as protein concentration increases, that's when the challenges can occur. And so I would say for anything that I'd consider a really complex or high protein, you may start to see that bias. And we see that quite often, where a really high protein sample on, say, the Tech Pro, for instance, will read about 10 to 30 milliosmol higher, and the XT will show that lower. So there is that difference, but it is able to handle most of the sample types. And I saw a question, and I appreciate this. So the question about the on-demand version, because of my speaking speed, I try my best to speak slow, but my natural speaking rate is quite fast. You will get a link to this. Also, again, my email will be included. Please feel free to reach out to me directly, and we can work through any other questions that may come up.
So 2 more just fluttering through, Eric. So replicants are not required for routine testing. Just if you have replicates, then 3 is the recommended. Is this correct?
Correct.
Okay, fantastic. And one more, is it possible that the same sample give different results from different osmometers? We have 2 different readings on 2 different models, 250 microliters versus 20 microliters.
Absolutely. It is absolutely possible. And that is actually called out in the compendial text itself. So it is truly acknowledged now that different osmometers can provide different results on the same sample. And that is essentially one of the big themes behind all this, is that technology selection matters for the sample. Then as you go into the deeper kind of the weeds of it all, it talks about how there's been a lot of improvements made in freezing point technology specifically, which is where some of these differences are coming up. Again, differences don't necessarily mean, if you're seeing a new instrument reading something different, that's not bad. It just means that an improvement has been made. As we improve our technology, then things get a little more precise.
Looks like that's it for the Q&A questions.
All right. Yeah, and we will absolutely go through the list too after, and but we are right at time anyway, so I will go through, put together any ones that are open and send out emails to everyone. But okay, so so I want to just pop in for biological formulation will not be non-volatile. So if there's not volatile excipients in there, vapor pressure can still be considered most reliable. There's some other challenges that can be associated with that method, which can make it a little more challenging, but you won't have that same problem where you're making some of the actual components evaporate. But there are some other method-based challenges. Again, happy to go through some of the data we've generated just to show the variability that you get from test to test with that. But you won't have that same issue that was illustrated before about the components evaporating or vaporizing, excuse me. Well, with that, thank you, everyone. I really appreciate the time today. Very excited about all these updates. Again, I will happily answer any questions that you send my way. And thank you all for your attention.